We've managed to build machines that can converse, paint, and write code, but keeping them running requires draining entire municipal power grids. This chart illustrates the scale of that power draw. A standard artificial intelligence data center scales into the megawatts, consuming massive electricity to train models. But a human brain performs staggeringly complex calculations on roughly 20 watts, a fraction of a standard light bulb. For decades, computer scientists have looked at that massive efficiency gap and asked a logical question. Instead of forcing sprawling arrays of silicon to clumsily imitate human thought, we might need a machine that actually processes information the way a biological brain does. The solution to the energy crisis in computing required abandoning purely artificial components entirely. A company called Cortical Labs stopped trying to write software that behaves like human brain tissue and started building processors out of the tissue itself. They call it the CL1. It's a fully functional, commercially available computer that operates using living human brain cells integrated directly with a digital interface. This is synthetic biological intelligence, or SBI. It merges the rigid logic of traditional hardware with the adaptable, living network of organic neurons. This system exists on the market right now, completely breaking our normal definition of a computer. To make a system like the CL1 work, you have to keep the processor alive. Cortical Labs refers to the physical setup as a body and a box. The core of the machine is a grid of 59 metal electrodes, acting as a playground for real biological neurons. These are grown from induced pluripotent stem cells, adult cells genetically reprogrammed back into an embryonic-like state to develop into brain tissue. Because these cells are alive, they require an entire built-in life support system. The hardware includes continuous filtration pumps, strict temperature controls, and precise gas mixing to maintain a healthy environment for the tissue. Once you have a living processor, you run into an immediate technical hurdle. You cannot type Python code into a petri dish and expect cells to execute commands. Since we can't write software for them, we have to leverage their natural biological instincts to get them to calculate and learn. The foundational proof for this method came from an earlier experiment called DishBrain. Researchers took a cultured network of these neurons and successfully taught them how to play the classic arcade game Pong. They accomplished this by tapping into a basic biological drive. Brain cells naturally want to conserve energy, so they constantly seek out order and predictable environments. Hitting the virtual ball rewarded the cells with a smooth, predictable electrical signal. Missing it caused a harsh, chaotic burst of static. To stop this chaos, the living cells physically reorganize their internal connections, adapting their structure to hit the ball consistently. This demonstrates what Cortical Labs calls the minimal viable brain. We aren't writing lines of logic. We are conditioning biological tissue with electrical stimuli to produce a desired outcome. Cortical Labs is currently scaling this architecture into full server racks, with each rack housing 30 individual CL1 units working together. They are rolling this out as Wetware as a service. A researcher anywhere in the world can log into a cloud platform and rent time on these biological networks to run experiments, completely offloading the complexity of maintaining the physical life support. A full rack of 30 biological computers draws less than 1 kilowatt of power. That is roughly the same amount of electricity needed to run a small kitchen microwave. This infrastructure makes a radically different form of computing globally accessible, sidestepping the massive, power-hungry data centers that traditional artificial intelligence requires. The immediate real-world value here lies in medical research. This new technology offers a vastly superior way to model complex neurological conditions like epilepsy and Alzheimer's disease. Historically, drug testing has relied on animal models or flat, two-dimensional cell cultures in a petri dish. These static environments lack the dynamic complexity of a living neural network, which often leads to promising drugs completely failing during human clinical trials. By migrating to biological computing, we open the door to highly personalized medicine. A lab could grow a neural processor using a specific patient's own cells, allowing doctors to test exactly how that individual's unique brain will react to a therapeutic drug before ever prescribing it. Integrating these living biological networks into modern robotics could give machines a highly flexible, truly human-like spatial adaptability, rather than forcing them to rely on rigid coding and massive training datasets. Naturally, using human tissue raises ethical questions. Cortical Labs works closely with bioethics committees to ensure compliance, noting that these systems are partial networks. Instead, they simply act as highly specialized computing substrates and possess absolutely no conscious awareness or ability to feel. The most efficient processor on Earth already exists inside our heads. The next major leap in computing requires us to finally learn how to collaborate with the biology we already have.